Okay, this week we are covering Chapter 5, Sensation and Perception. How does perception emerge from sensation? This chapter will discuss how various types of stimuli are detected, how the brain constructs useful information about the world on the basis of what has been detected, and how we use this constructed information to guide ourselves through the world around us. Sensory information is translated into meaningful signals. There are two elements of this. So the title of the chapter is Sensation and Perception. Sensation is the detection of external stimuli and the transmission of this information to the brain. Perception is the processing, organization, and interpretation of sensory signals. Here's a handy graphic from the book that lays it out. There's a stimulus. The example is a green light emits physical properties in the form of photons, light waves. The next step is sensation. You sense that this light has happened. Sensory receptors in the driver's eyes detect the stimulus. The third step is sensory coding. The stimulus is transduced, translated into chemical and electrical signals that are transmitted to the brain. And then there's perception. The driver's brain processes the neural signals and perceives the green light ahead. The brain interprets the representation of the light as a sign to continue driving. There are two kinds of processing going on here, bottom up and top down. Bottom up processing is perception based on the physical features of the stimulus. And top down processing is how knowledge, expectations, or past experiences shape the interpretation of sensory information. And now we're going to talk about transduction. First, there is sensory coding. This is when the sensory receptors translate the physical properties of stimuli into patterns of neural impulses. And then transduction. This is the process by which sensory stimuli are converted to signals the brain can interpret. I go back to a diagram of the brain here. These are the primary brain regions where information about vision, hearing, taste, smell, and touch are projected. The visual information travels in separate streams. What you see and where it is, from the occipital lobe, the visual cortex, to different parts of the brain for further processing. Here's another graphic from the book, lays out what we're talking about here. It's the five senses, the type of stimuli involved, the receptors involved, and the pathways to the brain. You want to look over this graphic. And now, quality versus quantity. The brain needs qualitative and quantitative information about a stimulus. Qualitative information consists of most basic qualities of a stimulus, whereas quantitative information consists of the degree or magnitude of those qualities. Example from the book here. Qualitative information, the sensory receptors respond to qualitative differences by firing in different combinations. A green light is coded by different receptors than a red light. Quantitative information, sensory receptors respond to quantitative differences by firing at different rates. A bright light causes receptors to fire more rapidly at a higher frequency than a dim light. Detection requires a certain amount of stimulus. Psychologists tried to understand the relationship between the world's physical properties and how we sense and perceive them. In psychophysics, this is a subfield developed during the 19th century by the researchers Ernst Weber and Gustav Fechner. It examines our psychological experiences of physical stimuli. All of this involves thresholds. An absolute threshold is the minimum intensity of stimulation that must occur before you experience a sensation. And a difference threshold, this is the minimum amount of change required for a person to detect a difference between two stimuli. And important here is Weber's law. This is the just noticeable difference between two stimuli, which is based on the proportion of the original stimulus rather than on a fixed amount of difference. Another graphic from the book here, talking about the absolute threshold. This is the level of intensity at which participants can correctly detect stimulus on 50% of the trials in which it is presented. The graph shows the relation between the intensity of a stimulus input and a person's ability to correctly detect the input. As an example, how much does the television volume need to change for you to notice? That amount of change is the difference threshold. Which leads us to signal detection theory. This is a theory of perception based on the idea that the detection of a stimulus requires a judgment. It is not an all or nothing process. Signal detection research involves a series of trials in which a stimulus is presented in only some trials. In each trial, the participant must state whether he or she sensed the stimulus. Radiology illustrates the subjective nature of detecting a stimulus. Here you see a doctor inspecting x-rays. Perhaps he's looking for abnormalities or something that might be of a medical concern for the patient. This is also a serious condition for looking for cancer in patients. All right, here's another graphic from the book that goes into greater depth on signal detection theory. There are 4 possible outcomes when a participant is asked whether something occurred during a trial. That is a hit, it's like it was there. A miss, you thought it was there and it wasn't. Now that's a false alarm. A miss is when it was there and you didn't notice. And a correct rejection is when it's not there and you know it's not there. Those who are biased toward reporting a signal tend to be yaysayers. They have many false alarms. Those who are biased towards denying that a signal occurred tend to be naysayers. They have many misses. Sensory adaptation. This is a decrease in sensitivity to a constant level of stimulation. If stimulus is presented continuously, the responses of the sensory systems that detect it tend to diminish over time. When a continuous stimulus stops, the sensory system usually responds strongly as well. There are many examples of this in daily life. Perhaps if somebody's running a vacuum in the room with you, you can kind of tune it out over time. That is sensory adaptation. This is the same as tolerance. Neurons are being stimulated, be it drugs or sensory input. Because of sensory adaptation, people who live near constant noise eventually become less aware of the noise. Pictured here are homes near London's Heathrow Airport. The brain constructs stable representations. In perception, the brain integrates millions of diverse neural inputs to produce stable representations. Working with just the electrical impulses it receives from nerves, the brain creates a rich variety of perceptual experiences. Although the brain creates stable representations, sometimes the resulting experience is quite unusual. Bill, who hates driving because of the sight of road signs, tastes like a mixture of pistachio ice cream and earwax. This is something called synesthesia, when objects such as letters, shapes, numbers, or people's names are joined with another sensory perception such as smell, color, or flavor. This figure is an artistic rendering of the color letter and color number associations for one person with synesthesia. Does ESP exist? Could people be able to perceive information beyond ordinary sensory information through extrasensory perception, or ESP? Many reports of ESP are supported only by anecdotes, not by valid evidence. There is always a reasonable explanation for something such like this. Nobel Prize-winning physicist Luis Alvarez found himself thinking of a long-lost friend from his college years. A few minutes later, he came across the friend's obituary in a newspaper. He calculated that the probability of thinking about a person shortly before learning that a person's death likely happens around 3,000 times per year in the United States. Put another way, about 10 people are likely to have this experience each day just by chance. A sender in a soundproof booth focused on a randomly generated image. A receiver in another room tried to sense the sender's imagery. The receiver was then asked to choose among 4 alternatives, one of which was correct. By chance, the receiver should have been correct 25% of the time. Across 11 studies, receivers were right about 33% of the time. Is this evidence of ESP? In a statistical review of many such studies found little support for ESP. In an fMRI study to examine brain functioning, evidence for the existence of ESP, researchers used a sender-receiver paradigm to look for brain differences between responses to the image. There were absolutely no differences in brain responses. This is strong evidence against the existence of ESP. Here's an example of the sender-receiver experiment. In Moulton and Coslin's 2008 laboratory study, the sender participant was instructed to think about a particular picture in order to send that message. The receiver participant was in an fMRI scanner and was shown a picture unrelated to the one the sender was thinking about. The receiver was also shown the picture the sender was thinking about. The fMRI was also recording the recipient's brain activity in response to both images. The receiver was then asked to identify which of the 2 images the sender had in mind. For a correct answer, the receiver earned $1, an incentive for trying to receive the sender's message. All right, and that concludes part 1 of chapter 5.